Uh, which problem?
Okay, well this one's quick. For 4 and 5, they ask you to write the balanced equation, and they give you like a visual of the molecules. I don't know if it's just my iPad, but it doesn't tell me what each molecule is. It doesn't have like a chart.
Well, they're using the standard coloring scheme for these. And so in the standard scheme, what we have is yellow, is like sulfur, and then they have other colors. It's not always, strictly adhered to, but white is usually hydrogen, blue is nitrogen, so this is N2H2. N2, actually H4. N2H4 is dinitrogen tetrahydride. And then this would be oxygen is red, so this would be N2O4. And then red would be oxygen and 2 hydrogens. This would be water, and this would be N2, nitrogen gas.
All right.
Okay.
So I did know what they were. I just got it wrong.
Okay.
And then number 8. I just don't want to do that one. And I think there's one that says trust.
Number 8.
That there was on the last semester.
Yeah. This is a very common problem that we have. So iron ore contains iron 3 oxide and other stuff. The iron 3 oxide is heated with excess carbon, coke. Metallic iron and carbon monoxide gas are produced. And so what we have is the other stuff is inert when we add excess carbon. And so we just target the reaction to this. So iron ore is impure iron 3 oxide or rust. When iron 3 oxide is heated with an excess of carbon coke, metallic iron and carbon monoxide gas are produced. From a sample of ore weighing 920 kilograms, 522 kilograms of pure iron is obtained. So in this particular problem, what is the mass percent of what is mass percent? Well, we could do different mass percents. So for example, I could have asked you, what is the mass percent of iron in this ore? The mass percent of iron in this ore would be 522 kilograms of iron, pure iron, divided by 920 kilograms of ore. So it'd be more than 50% here, maybe 60% roughly iron. But what they're asking is they want the ore component, iron 3 oxide. So we have to do a little bit of stoichiometry. So we just go from kilograms of iron. I would do this myself. I'd go kilograms of iron to grams of iron. Grams of iron to grams of, or not to grams, but moles. We could use a percent by mass too. Sometimes the percent by mass data is already collected. So if we know the percent by mass, Fe2O3, there, it's a possibility. And so let's see how they do it. It looks like they use the percent by mass. I wouldn't have used the percent by mass here. I would have done it like this instead. Let's see if Word is going to work. I would have just went 522 kilograms of pure iron, and then go to grams of iron to moles of iron. Moles of iron, then I would use the mole ratio of the formula to get moles of Fe2O3. The mole ratio here is that we have 1 mole of Fe2O3. This is from the formula. We're going to have 2 moles of Fe. So that's not from a balanced chemical equation, but it's just from the formula: 2 irons, 3 oxygens. So, and then I'll go to grams of Fe2O3 and then kilograms. Actually, I'm going to erase this here. And so then the percent Fe2O3, we could do this all in one step, or we could do it in a couple of steps. So once we get the kilograms of Fe2O3, we'll just divide it by kilograms of ore times 100%. We could do something like that. But a more common percentage would be the percent iron in the ore, because that's what people are interested in. They're interested in the iron, not necessarily the rust or the Fe2O3. Okay. All right. Any other questions? Mm-hmm. Yeah, that, let's see. That is not a chemical reaction, and so what we do in that particular case is, if you take chlorine aqueous and mix it with chloroform, chlorine is fairly nonpolar, and water is very polar, but chloroform is fairly nonpolar. You can tell it's fairly nonpolar because water and chloroform don't mix. They form two separate layers. It's like oil and water. Even though this, when we do the Lewis structure, this appears to be a polar molecule, quite polar, because when we do the Lewis structure, this has a tetrahedral structure to it. And so if we were to draw out the Lewis structure for this, I'd say it's polar. I'd say it's polar because we got bond dipoles pulling towards the chlorine, and the net molecular dipole should be down like this. So it looks polar. But when we mix it with water, they don't mix. And so this is a physical process, but this physical process we're going to represent using an equation. We do equations for both physical processes and chemical processes. And so it looks polar, this molecule, but it is nonpolar. Just based on its observational behavior, it behaves as if it's nonpolar because it doesn't want to dissolve in water. And so we're going to have chloroform, but now the chloroform, if we do a proper extraction, will be extracted into the chloroform layer. The chlorine will be extracted in the chloroform layer. So this is a physical process. It's called solvent extraction. In solvent extraction, you're taking the solute out of one solvent and extracting it into another solvent. And the other solvent it should be more soluble in. So chlorine, being nonpolar, is more soluble in chloroform than it is in water. We can't dissolve that much chlorine in water. Okay, so that brings up, what do you do in the reactions when you mix it? So for example, if we took chlorine plus potassium bromide plus chloroform. Chloroform is a liquid. Here, liquid, and so we'll write liquid there. Whereas these two are aqueous. What happens? And so when we have a reaction like this is a two-step process here. The first step is the chlorine is going to oxidize the two bromides. We could use the Charp method here, or we could use, probably the Charp method is fine. And then when we do this, the chlorine oxidizes the bromide, taking the electrons, and we end up with two chlorides and a bromine. We should talk about this in the lab. but this is related to lecture, so I guess I'll do this. And then for the solvent extraction, what we're going to do is we're going to show an additional arrow here with CHCl3 liquid addition. And so we're going to take bromine aqueous, and then we're going to make bromine CHCl3 here. We're not going to solvent extract the chloride. The chloride is just too polar to dissolve in the chloroform. The chloride's a monopole, what we call it. It just has a single charge.
Why do you write the chloroform as like a subscript next to the chloride?
It's just to say it's this. We're taking bromine from the aqueous phase into the chloroform phase. And so
What is that?
aqueous means what? Dissolved in water. What this means is it's dissolved no longer in water. The bromine is now dissolved in chloroform. That's why we write the subscript there. Subscript tells us the state, and the state could be a mixture. Aqueous is a mixture. This is also a mixture.
Who does that? So if it dissolves in chloroform, has to be in non-chloroform.
It has to be non-polar to dissolve in chloroform. The solvent extraction is a very common technique. This is one of the first things you learn in organic chemistry lab is the solvent extraction. You have a special thing, which is very expensive. It's called a separatory funnel. Separatory funnel, you have that chloroform layer stuck at the bottom, but sometimes in organic lab, what we want is, we don't want it stuck at the bottom. We want to extract it. Let me see. No, I'll just. So we have something called a separatory funnel. Ooh, you get 20% off. You might need that because if you break one of these, how much are these now? $337 for a small, $450 for a large. If you break one, and people break these all the time, it's going to be a big bill. Organic bills can be very large, like in the hundreds of dollars, or many hundreds of dollars. Break some of the expensive glassware. But anyway, the chloroform would settle down to the bottom, so an easy way to do this is just to drain it out, and then you can separate the chloroform layer from the other layer. Or if you have oil, the oil would float on the top, so you can drain the aqueous layer down here. And so it's an easy way to separate two layers for a solvent extraction. It's a very, very common technique. Using the separatory funnels, you use this all the time. Maybe they need to make them out of plastic, polycarbonate or something. I don't know. It's so expensive. $450. I broke one, but it was only like $200 at the time, maybe, or $100. I don't remember. My total bill after organic chemistry is like $250 in breaking glassware. Yeah, it's pretty expensive.
How is that one more like special than just a regular funnel? Like if things are just gonna floating.
No, because you could stop it any time you want. Regular funnel is just going to continue draining due to gravity. This one you can close. This is like a direct stopcock right here, so you can just close it when you want. You drain off the bottom. It allows you to control it. It's not a funnel, it's just separating two liquid layers. You have two immiscible liquids. Immiscible means they don't dissolve in one another. And then you can separate the two immiscible layers. Let's say you have oil and water. This would be great. Let's say there's an oil spill, you scoop it up and then you can separate it using a SEP funnel, but it's not practical. Let's say if there's an oil spill you want to get rid of. There's been like a bunch of oil spills growing. in Santa Barbara, there's been a bunch of oil spills, around here too, I'm sure. But, you know, how do you clean up all the oil? All the birds get coated in oil and stuff. And so if somebody developed something giant like this, it'd be pretty easy to separate. Put all the ocean water in there, and then you can just leave the oil in the sep funnel and have all the water down at the bottom.
But it seems like the pyramid system doesn't seem that complicated. It just has a whole everything.
It's not that complicated, but glass blowing is complicated, you know. And this is a ground glass joint here, or it might not be. The top is a ground glass joint. And that ground glass joint requires some machining to do. It's a glass stopper machine on the top, and it's very tight fit. And so that's actually made using a machine that grinds the glass, smooths it out. And then, you know, glass blowing is not easy. I've had much more expensive pieces of glass than this, you know. At all the major departments, they have a full-time glass blower. And so you can ask them to make you a custom piece of equipment. So I've had lots of custom pieces made, like thousands of dollars worth of custom glassware made. You know. Fortunately, I didn't break any of those. But, you know, $250 is cheap in the relative scheme of things, because there's this rumor going around the chemistry department at UCLA that one of the grad students accidentally dropped or lost, or something happened. It was $36,000 worth. It was only like 100 or 200 milligrams worth of chemicals, and it's gone, you know, lost due to poor technique. Anyway, so that was the gossip around the chemistry. That type of gossip happens. All right, any other questions? I need to get through chapter 7. I want to do all of chapter 7 on exam 2. So we have that little bit of extra time rather than splitting it up. So we're talking about objects. You know, when we have an object, if you add energy or you remove energy, it just changes the temperature of the object. And how is the energy related to temperature? So that's what I want to talk about now. This is usually this is going to be whenever we think about temperature changes, we're thinking about changes in kinetic energy, and when we have exchange of energy in the form of kinetic energy, we call it heat. You know, either heating it up or cooling it down. It's all labeled heat, whether you warm it or cool it. And so the energy here actually, let's talk about objects. We're going to talk about energy in the form of heat, you know, which is given the symbol Q, is related to temperature by the specific heat or the heat capacity. So this is for objects, and so let's take a look at the heat capacity here next. And so when we think about heat, it's just this thermal energy transfer. You know, it's kinetic energy transfer from a hot object. It's like if you touch a hot object, you're feeling that kinetic energy. And that kinetic energy is going to be transferred to your skin. is kinetic energy. It's proportional to temperature. Temperature is a direct measure of kinetic energies. So in other words, temperature is directly proportional to kinetic energy, average kinetic energy. It's an intensive property. Energy is always an intensive property. And so it depends on how much energy you have. You could have lots of energy or a little bit of energy. It's intensive. It's an intensive. What does that mean, intensive property? Is it an intensive property? We're talking about thermal energy is not an intensive property. Thermal energy is an extensive property, right? When it's related to temperature, it's an intensive property. But in general, energy is extensive. I mean, you can run out of energy. And so energy depends on the amount that you have. Heat is the exchange of this kinetic energy here. Work is different. We have different types of work that can be done. We could have mechanical work, like pushing an object over a distance, some force. Mechanical work. It could be sound, like pushing air molecules with some force. And so mechanical work could be like your car engine. It can do mechanical, if you have a car. Or a bicycle. But we have other types of work, too. The other type of work is electrical work. Etc. And so, energy changes, which we call delta E, is equal to the heat exchanged plus the work exchanged between the system and surroundings. So if there's been an energy change, because the first law of thermodynamics says that the energy is constant, the energy before and the energy after. So what we're looking at is the energy change of the system.
Wait, so when is energy an intensive property?
It's an intensive property for with temperature. With temperature, here it doesn't matter how big this room is or how small this room is. If it's at one temperature, let's say room temperature 25, it's colder than 25 today. But if it's at 25, then the average kinetic energy is an intensive property. That is the average kinetic energy. And that goes for any object in thermal contact, because the air is in contact with this camera. It's in contact with the countertops. It's in contact with everything. So if it's in thermal contact with that, then that means these must be at the same average kinetic energy as well. In other words, these must be at the same temperature. Now that's going to be a little hot. This might be a little hot because of the light. But otherwise, everything's at the same average kinetic energy. So the average kinetic energy and temperature will be an intensive property. And so what you could have is, you could have some water here. But energy is also extensive because it depends on how much water you have, and that's going to give you the total energy contained in this. So we'll talk about that next here. And so in general, we think of energy as being extensive, but when we're thinking about temperature, everything at the same temperature has the same average kinetic energy. And so in that respect, it doesn't matter how big or small the object is, it's going to have the same average kinetic energy.
So then when is kinetic energy not
When it's always, kinetic energy is thermal energy.
So how come, like, in general, energy is extensive? Because it rents out?
Let's say you need to put out a fire. Does it matter how much you use? How much water you use? Let's say if I want to put out a fire and I just use a drop of water, is that enough? And so in that respect, it's an extensive property. It's going to depend on how much water you use to extinguish the fire. Let's say you need to cool down. Let's say you need to cool down. There's a particular problem. I don't know if it's still, I don't think I assigned it as homework. Let's say you want to cool down the interior of your car. It's really hot. And so they have some alcohol spray that you can spray in there, and it cools things down a little bit as the alcohol evaporates. But does it matter how much alcohol you spray in the car for the evaporative cooling? Yeah, it matters. And so in that sense, it's extensive. Because the more you have, the more energy it can absorb. The same thing with water. If you want to cool something down with water, it depends on how much you have. You know, the more you have, the more you can cool down, basically. And so there it's extensive. And so thermal energy is going to be extensive. It depends on how much you have. So if we have 50 grams of water at 25 degrees C, that has less energy than 100 grams of water at 25 degrees C. It has half as much energy, even though they're both at the same temperature, even though they both have the same average kinetic energy. I think when we do some examples, you'll see. These are the slides I just used. I would have organized these slides differently, but I'll just use it for the book because it follows the book pretty much. But internal energy is transferred between a system and its surroundings as a result of temperature difference. That's internal energy is heat is transferred. Anybody recall the symbol for internal energy from last time? No? Capital U. Is transferred between a system and its surroundings as a result of a temperature difference? I say can be transferred. It's not always transferred as a temperature difference. Internal energy can be transferred as heat. And so we can just summarize this. This just says internal energy, U, can be transferred as heat. Delta U. If it's transferred as heat, heat flows from a hotter to a colder object. The temperature can change, of course. Phase may also change. If phase changes, we don't call that. Do you see this isothermal process? Do you know what iso means? Same. Thermal means temperature in this context. And so phase may change an isothermal process. We call this the processes. All processes are going to be treated as isothermal. We do that to simplify the math. This makes the math easier. And most are. All processes are going to be treated as isothermal. Makes math easier. And some are already isothermal processes. So what isothermal means is that the temperature does not change. So as you recall, we have to start dealing with some equations now. When we look at U is equal to the sum of the what? U is equal to E, which is equal to the sum of the, yeah, kinetic energy plus the potential energy. And we have delta U. Delta U is going to equal the change in kinetic energy plus the change in potential energy. So if this is transferred as heat, and so for basically it boils down to this. And so I'm going to summarize this slide as this. For objects, delta U is equal to delta E K, which is kinetic energy, plus delta PE, which is potential energy. For objects, what we do is we don't change the potential energy. That is, the delta PE is 0. So the only change is in kinetic energy here. And that change in kinetic energy is going to be manifested in the form of heat, Q. And the relationship between heat and temperature is given by this equation here. It's equal to the amount times C times delta T. This is the amount of object, usually in grams, sometimes in moles, sometimes in other units. C is called the heat capacity, and delta T is the change in temperature. So when we have an object, the potential energy doesn't change. The only change is the change in kinetic energy. This change in kinetic energy is going to be manifested as a change in temperature, and the relationship between energy and temperature is the heat capacity here. Heat capacities we can measure or we can calculate theoretically. I'm sorry? Amount. AMT is the amount of object.
That's in EMT or AMP?
AMT.
How many objects?
Amount of object in grams, moles, or number. If we have it in grams, then this equation is Q is equal to M, the mass, times C times delta T, MC delta T. This is a very familiar equation in intro. However, we don't always measure it in grams. Sometimes we measure it in moles. So if the amount is in moles, we use a different heat capacity. If we have the heat capacity in grams, we could use something called specific heat. If we have moles as the amount, we use the heat capacity as the molar heat capacity. If we have it in number of objects, then it's just the heat capacity of an object. And delta T is the change in temperature. If it's a process, then what we do is we don't allow the temperature to change. Isothermal means the temperature doesn't change. If the temperature doesn't change, was there any change in kinetic energy? No. And so the delta E sub K is 0. That means all the change is in terms of potential energy here.
We just established that delta U, the potential, delta potential energy is 0. Like on that side. With the
Yeah. This side here?
the pink that has like the arrow.
Yeah. Yeah. Here, it's the opposite here. So now the pink arrow is on this side. Kinetic energy doesn't change. Let me give you some examples. I'm going to have a number of examples we can look at. And the change is strictly in potential energy.
Well, when would you use that versus that?
If it's a process, we use this. If it's an object, we use this. Energy is extensive, so we need amounts. So I forgot how much I had, 50.0 grams of water at 100 degrees C. So I have some kind of arbitrary internal energy scale here, U or E. And then I have my 50.0 grams of H2O liquid at 100 degrees C. All right, one thing, I can cool this down to room temperature. And so I'm going to get 50.0 grams of H2O liquid at 25 degrees C. So what happened there? What happened there is there's a change in internal energy. And so there's a delta U here. When we look at the delta U is equal to a change in kinetic energy plus a change in potential energy. But when we look at the potential energy is chemical potential energy, which I talked about last time. Was there any change in chemical potential energy here? No, because it's just still water. And so water is just water. And so there's no change in chemical potential energy here. And so the change is strictly in kinetic energy here. And this is equal to Q plus W. Was any work done, like mechanical work or electric? Did we generate any electricity? Did we pull up any weights? Do anything like that? No. And so this change in required zero work. There was no work done here. And so this change in internal energy is just equal to Q is equal to M C delta T. So we could figure out how much energy in heat or in delta U or delta EK we did, because delta U is equal to delta EK, which is equal to Q. And so one of the hard things about thermodynamics is keeping track of all these relationships, you know, and that's what makes thermodynamics difficult, because you have all these relationships. So the amount we can use in grams, so this is 50.0 grams, that's the amount. The specific heat of water can be determined from experiments, 4.18 joules per gram degree C, and delta T here is going to equal, what is delta T? T final minus T initial. So T final is 25 degrees C minus T initial is 100 degrees C. And that's Q. All right, so if we calculate it here, we have 50 times 4.18 times 75. And that gives us minus 15,675 joules. You just got to make sure the units cancel out. Grams, degrees C cancels out. And then we just convert this into kilojoules. So minus 15.67 kilojoules here. Actually, we should only have 2 sig figs, sorry. This should be minus 16 kilojoules. We get 2 sig figs from because the temperature changed. Only 2 sig figs. It's 75 degrees. Minus 16 kilojoules. All right, what happens if we add energy to water liquid water at 100 degrees C? When we add it, it's increasing energy here. And so we're going to end up with, do you know what we're going to end up with? 50.0 grams of H2O gas. When you boil water, does the temperature increase continuously or does it stay constant? It increases. Yes? Or it stays constant? It stays constant. So that's intensive. The boiling point of water is an intensive property. It doesn't matter if you boil a lot of water or a little bit of water, it's the same temperature. That's intensive. Extensive would depend on the amount. Here it doesn't depend on the amount. All right, so delta U is equal to delta EK plus delta PE. Was there any change in kinetic energy? We start off at 100 degrees C, we end at 100 degrees C. Was there any change in kinetic energy? No. All the change is potential energy. And is there really a change? It's still water, isn't it? But yeah, we have liquid water and we have steam. You know, steam, they say, has different potential energy. Steam. Steam burns are much worse than liquid water burns. Have you heard that? Steam causes much more severe burns. And there's thermodynamic reason for that. It causes much more severe burns because when steam condenses, it releases a lot of energy. When you boil water, how long does it take to boil a pot of water? How much energy do you have to put into that pot of water to get it to boil? Quite a lot, right? And since energy is conserved, what happens is when that steam condenses back into liquid water, you know what happens to all that energy that you used to boil it? It's released. And if it gets released into your skin, it causes, severe burns, 2nd, 3rd degree burns. And so we can figure out how much that is here. And so let's take a look. I have to use some data a little bit farther ahead. Actually, I don't know if I have it in this chapter. Doesn't look like I have it. $2,260 joules per gram. 2260. How much energy it costs to boil water is the amount times what we call, in this case, we're going to use something called the heat of vaporization. We're going to put quotation marks around heat. 2260 kilojoules per gram. And so we have 50 grams. So I'll do 50 times 2260. This gives us 113,000 joules of energy, which means it's 113 kilojoules.
I thought it wasn't.
I'm sorry?
I thought it wasn't.
Oh, it is, oh, yeah, you're right, it's already in kilojoules. This is kilojoules here. Okay, when the system gains energy, it's positive. When the system loses energy, it's negative. And so we just drop down in energy or we go up in energy. The drop down here is only 16 kilojoules, but the increase is, this is not the scale. It's 113,000. So if we drop 16 down, we got to go up 113,000. So what I'm going to do is I'm going to split this because this is not to scale. This is actually, it would be way up, way up there in terms of energy. Do you see that? And so it's going to be much higher in energy. And so what we do is we handle this differently. Once we boil all the water, then that's it. We're done. However, once we cool the object here, we still have the object. It's just a colder object. But this is a process up here. The process has a finite lifetime. An object has like an infinite lifetime. And so this is the process. And the process is boiling. And once we finish boiling, there's nothing left. Down here, this is an object in which we cool the water. And we still have the object left down here. It's just colder. So we can do it like this. Let's say I have 523 grams of iron solid. What would I want to know if I have some iron solid? I would want to know at what temperature this iron is. And so let's say this iron is at 315 degrees C. Then this iron has quite a bit of kinetic energy. Do you see that? It's pretty hot piece of iron. But does it have much potential energy? Well, no, it's just an piece of iron. Now, if there were oxygen around, then it has potential energy because what can happen to the iron? It can become oxidized. It can rust. And so if there's oxygen around, I'd worry about it. I'd worry about the potential energy here. But if it's just a piece of iron, then that's just an object. You know, nothing should happen to it chemically, as long as there's no air. And we can't assume that there's air there. And so here, we're still going to have 523 grams of iron. But let's say we cooled it down to room temperature at 25 degrees C. So this is an object. When we think about an object, then we think that the kinetic energy initial and the kinetic energy final are going to be different. But the potential energy initial and the potential energy final will be the same. So these are equal. These are not equal. All right, let's say I have some methane gas and oxygen gas at 25 degrees C. I could treat this as an object. For example, if I treat this as an object, I might warm it up or cool it down, right? Or I could just let it react, because this has potential energy. It has the potential to react to form what? Yeah, and so when you burn methane with oxygen, what happens? You get a flame, and the flame gets extremely hot. You know, how hot does it get? Well, you know, methane, they're different flames and they're different flame temperatures, and so it depends. You can get hotter or colder, but it gets very hot, like extremely hot, 800, 1,000 degrees C. It gets extremely hot, but what we do is we wait for it to cool down. And so when methane combusts with oxygen, the temperature skyrockets, but what we do is we let it cool back down to 25 degrees C. So what we see is we just see the initial here and the final here. We're just going to bypass this whole thing. This whole thing is going to skyrocket in temperature, but it's not going to stay hot forever. And as it cools down, do you know what it does? It releases heat to the surroundings. So what we want to do is we want to figure out what is the maximum amount of heat that's released to the surroundings. If we want to know the maximum amount of heat that's released to the surroundings, then we got to let it cool all the way back down to the starting temperature. If it doesn't, then we haven't released all the heat. And some of that heat is contained. And so this is initial and final. This is a process here. And what we do is we do at the same temperature. So we allow it to cool, and we want to make sure the starting temperature and the ending temperature are equal. And so the initial temperature should equal the final temperature. But we don't care what the intermediate temperature was. The intermediate temperature could have skyrocketed. It's fine. The reason we do that is we don't want two equations. Because when we heat and cool objects, that's one equation. And then we have another equation for processes. And so to keep our math simple, we always do it this way. Processes always involve, like isothermal, we call this isothermal scenarios. In other words, for processes, keep the temperature the same so we don't have to deal with the heat capacity of methane, the heat capacity of O2, the heat capacity of CO2, the heat capacity of water. We don't want to deal with that. So keep the temperature the same, and therefore it's going to be a lot easier to deal with our delta U. Our delta U here is only going to be a change in potential energy. Over here, our delta U is only a change in kinetic energy. So here, we don't want to cool it down and then do a whole bunch of reactions at the same time and confuse everything. We just want to keep all our calculations as simple as possible. And this is the way to keep your calculations as simple as possible. And so this is why I say there are two types of systems. First, you have to define the system. Is the system an object or is the system a process? That's the first thing you have to do. And then you know how to handle it after that, because we'll do examples of how to handle objects and how to handle processes.
Are processes always going to be like chemical reactions?
No. Our process is always going to be chemical reactions. No, they're not, because here's a process that's not a chemical reaction. This process is the process of boiling water. So we start at 100 degrees C and we end at 100 degrees C. Of course, we could have boiled the water and then heated up the steam to like superheat it. And so we could have said, okay, I'm going to boil 50 grams of water, and then I'm going to convert that 50 grams of water into 50 grams of steam at 150 degrees C. You know, but we don't want to do that in one step. Well, if we're going to do that, we're going to do it in two steps. So the first step is the process of boiling the water. The second step would be the process of heating the steam up to even higher temperatures. And so we're always going to keep it separate.
So for processes, we keep the temperature the same.
Yeah, for processes, always keep the temperature the same. If you're starting to mix the temperatures up, sure, you could do that, but then you got to keep track of all the equations in your head. I mean, it's not a problem. It's easy to do if you've done it a bunch of times. But when you're learning it, always keep it separate. Otherwise, you're just making more work for yourself. And even even if you've done it a bunch of times, most people will do it in multiple steps rather than trying to cram it into one equation. They'll just say, okay, this is calculation for step 1, step 2, step 3. And then they'll use something called Hess's law. Hess's law is you just add up all the steps and you'll get the total energy.
And then, so for objects, we keep the potential energies then?
Yeah, for objects, the potential energy is always the same. It's just a change in kinetic energy. And change in kinetic energy means the temperature changes.
I know you said that we're not like as interested because it would get kind of complicated on the like to what like temperature the reaction got to, but would it be important to know?
Yeah, it's important to know, but you would treat it as two separate problems. One, you would dump all the energy. You would dump all the energy. Where does all this energy go? Energy is conserved. Energy is neither created nor destroyed. So if you define your system as this process, where does all the energy that gets dumped goes? Into the surroundings. And now it depends on what your surroundings are. If your surroundings is a pot of water, how hot does the pot of water get? Well, once we know how much energy is dumped into the surroundings, then we just take how many grams of water do we have and how much energy do we need to put into it. And so we treat it as a separate problem. If your surroundings is a room full of air, then how hot is the air going to get? And so all we need to know is the heat capacity or the specific heat of air, and then we can easily calculate it. So we treat it as two separate problems. Once we dump all the energy as much as we can from the potential, and then convert that into kinetic energy, but it depends on what the objects you're heating up are. That's how hot it's going to get, you know. And usually, in this case, it's like a Bunsen burner. You could figure it out. You know, you could figure it out because now the process is, once it's done burning, and we've released all the energy, then everything that remains is surroundings. So the CO2 and water used to be part of the system. Now it's part of the surroundings. So we figure out how much CO2, how much water, how much air, and then we can figure out what the temperature is going to be at the end. But we got to treat those separately. We don't treat them together, otherwise we get things that are too mixed up. So of course, in other words, we can have an object and process, but we don't want to because it makes the math more difficult. We try to keep the math easy. Joule is the most common unit. 1 joule, you know, 1 joule is the amount of energy needed to lift 1 kilogram by 1 meter against the force of gravity. So that requires 1 joule of energy. 1 calorie, do you know how 1 calorie is defined? Yeah. A calorie, the definition of the calorie is the quantity of heat required to change the temperature of 1 gram of water by 1 degree C. And because the density of water changes a little bit, it's between, I think, 4.5 and 5 degrees, or 4 and 5 degrees. 4 to 5 degrees, I think. But it doesn't change much, so we just use it. You know, if you want the exact definition, that's it. And so it takes about 4 joules to equal 1 calorie. And so this is defined mechanically, and this is just defined as heating water. The transfer of kinetic energy. We also have something called the food calorie. I might as well talk about it here. And it has a capital C. We use this for food, and it's equal to or defined as 1,000 chemical calories. So if you have a 1,000 calorie diet, then that's actually, that's 1,000 food calories. Well, if you have a 1,000 food calorie diet, that's 100,000 chemical calorie diet. So in calories for food, they don't want to say kilocalories. They probably should say kilocalories instead. but it's too much effort. And so that's why they have a new unit called the food calorie. So the heat capacity is the quantity of heat required to change the temperature of a system by 1 degree. But it depends on the system. And so this is this is the system here. And so we have different systems here. So C, the heat capacity, is the quantity of heat required to change. Let's say if it's by gram, then we'll have the mass, M delta, well, MC delta T, yeah, delta T. This is the mass. So this would be like grams of water. This is called the specific heat. We'll talk about these. But the heat capacity could also, rather than grams, we could just do moles times delta T. This is called the molar heat capacity. But let's say you have a brick wall. Do you want to weigh how many grams your brick wall weighs? No. Do you want to convert the number of bricks into moles of bricks? Whoever is going to use a mole of bricks. And so what we often do is we'll just say Q is equal to the object, like a brick, or mug. You know, if you have a mug, a coffee mug, you want to figure out, you know, how much heat your coffee mug absorbs. Then this would be Q per coffee mug times delta T. Let's say you have 10 coffee mugs. And so it'd be, 10 objects. Or let's say you have 1,000 bricks. Then this would be the Q per brick per delta T. So how much heat do you have to add to the brick to get the temperature to change? And so that would be the number of objects. So we could do that. And so this system here, what they're doing is they're calling the system an object here. And they're just saying per object here, but they didn't write it in here. But it's there. And so in other words, they're treating the system as an object. But they should have written it in there. So the molar heat capacity is given this symbol, C sub M. That M is kind of confusing because the M, is supposed to represent molar. And then P, you know what P represents? At constant pressure. The amount of heat, oddly enough, depends on if we do the reaction under constant pressure. Constant pressure would be like thinking in terms of Avogadro's. Remember Avogadro's? Versus constant volume. Constant volume would be in thinking in terms of Dalton's. And that's very important in thermodynamics. We need to know, are we doing this under constant pressure or constant volume? Because it makes a difference in the amount of heat you can get or require. And so that's the molar heat capacity. It's just per mole. And then we have the specific heat. The specific heat is the gram heat capacity per gram. And so this is given CP. Actually, there are other symbols that are used for specific heat. And then we have the heat capacity of the object. I should add that in here. The most common object we're going to use? One of the most common objects is an instrument that's designed to measure heat and temperature. And that object is called a calorimeter. Calorimeter measures how many calories or how many joules it takes to increase the temperature. So there's a thermometer on the calorimeter that we can use. And so Q is equal to should I say? Q is equal to the calorimeter times C times delta T. But how many calorimeters do we usually use? Only one. And so we only use one calorimeter. We don't use 2 calorimeters. It's like, how many thermometers do you use to measure the temperature of water? Usually just one, right? But if you put in 10 thermometers into your water, do you think that has the potential to change the temperature? Yeah, if the thermometer is a different temperature than your water, it could. But anyway, here we just use one, so this equation is often simplified into C delta T, since we only use one calorimeter. And so oftentimes you'll see this equation written like this. The amount is just 1. Q is equal to 1C delta T. And because we only ever use one object. Does that make sense? This is the first law of thermodynamics. And so we're going to start doing some calculations based on this. We want to calculate the amount of heat that's transferred between the system and the surroundings. And so, or the energy, you know. And so here, we have to know that the total energy is constant. So any heat that's gained or lost by the system results in heat that's lost or gained, the opposite. And so the negative just means opposite charge, or not charge. This is not charge. Opposite direction. So if the system's positive, the surroundings will be negative. If the system's negative, the surroundings will be positive. And so it just has to be the opposite sign. That way they add up to 0. We also have the sign convention. So Q of the system is less than 0. That means heat was lost or gained. If it's negative, means it's lost. That means Q of the surroundings must be greater than 0. That means the surroundings must gain. If Q of the system is greater than 0, that means heat was gained. But where did it gain it from? It must have taken it from the surroundings. Therefore, the surroundings must have negative. It must have lost. And the quantity of heat is the same. There. And so if the system gains 10, the surroundings must have lost 10. It's zero sum. There's no win-win. It's got to be win-loss only. So what we're going to do is we're going to define our system. The system is going to be 150 grams of lead at 100 degrees C. Looks like that. That's what it looks like. It looks like the water is boiling, so this must be at 100 degrees C. We'll go 100.0 degrees C to get the right precision. And so this is our system. Then we're going to take our system and dump it into this. This is called a calorimeter here. And this looks pretty well insulated, right? So our calorimeter currently is at 22.0 degrees C, and it contains 50.0 grams of water. And so what we're going to do is we're going to take all this lead and dump it into this water. And what do you think is going to happen? Well, the lead's going to cool down, right? And the water is going to heat up. And so what we do is we measure the final temperature of our calorimeter. When we measure the final temperature of the calorimeter, it's 28.8 degrees C. So this is what we're going to do. Our system is this, and our surroundings is this. So we're going to use the first law of thermodynamics. The first law of thermodynamics says that let me just do this here. It just says Q of the system is equal to minus Q of the surroundings. In this case, this is going to be minus Q of the calorimeter. So what does the calorimeter, what is it comprised of? Actually, we're going to simplify it. The calorimeter is comprised of 50.0 grams, so it's going to be minus Q of the water. We have 50.0 grams of water at 22 degrees C. What else is going to absorb energy? Q of the beaker plus Q of the air that's trapped in there plus Q of the thermometer plus Q of the insulation. The insulation shouldn't absorb much energy. I mean, that's why it's insulation. But it could absorb a small amount of energy. Plus, do you see it's not really well sealed? So some heat can leak out of here. Do you see that? And so I'm going to add one more thing here. Plus Q of the rest of the universe. We don't know what's out here. If we knew what's out here, then we can list it. But instead, I'm just going to call it the rest of the universe. So what we do is we treat this whole thing as one object. The reason we do that is because we can do something called calibration. That is, we can dump a known amount of heat in here and then see how much the temperature rises. So Q of the calorimeter is equal to the amount of calorimeters. How many calorimeters do we have? One. Are we ever going to have multiple calorimeters, like 10 calorimeters? Never. And so what your book likes to do is just like to forget that it's just one. And so I'm not going to put in the amount here. It's 1 calorimeter times C of the calorimeter times delta T. So the first step is a calibration of the calorimeter. If we do a calibration, then C of the calorimeter is equal to Q over delta T. And so all we'll do is we'll dump in a known amount of heat. Let's say we put in 1,000 kilojoules and then measure the temperature change. And therefore, we could say that for every degree C temperature change, that's going to require this many kilojoules. Does that make sense? And therefore, if we have an unknown amount of heat and we see the temperature rise, okay, let's say the temperature rose by 10 degrees C, then we know it must have been 10 times the energy. And then we can figure out how much energy that is. Does that make sense? No? Yes? So in other words, we want to know, it's like a brick. The first thing is, if you have a brick and you want to know how much the temperature is going to change when it absorbs this much energy, then the first thing we do is calibrate it. So we'll take the brick and we'll heat it up with a known amount of energy and see how much the temperature change. Some bricks, the temperature changes very little. They absorb lots of heat. Other bricks, the temperature changes rapidly. They don't absorb much heat. It's like I don't know, like after sunset, you go to a brick wall, and do you feel the heat radiating off brick walls sometimes? That's because it's absorbed a lot of heat, during the daytime. And rock walls do the same thing. So it's the same thing here. We're treating this whole thing as one big brick, and how much energy does that big brick absorb? It's heat. This is the normal way we do it.
What's that thing called?
Calorimeter. Calorimeter is a device to measure heat and temperature changes. It's actually a device to measure heat. Because what you do is you calibrate the temperature change with a known amount of heat. Therefore, if you have an unknown amount of heat, but a known temperature change, then you can figure it out. And so this measures heat.
Does that say a calorie is a kilojoule delta T?
This is C of the calorie. This is the heat capacity of the calorimeter. And so any heat that's lost by the lead will be absorbed by everything else. Does that make sense? But we're going to make an assumption to make this problem simpler. To make this problem simpler, we're going to assume that the beaker doesn't absorb much heat. The air that's trapped in here doesn't absorb that much heat. The insulation doesn't absorb that much heat. And the thermometer doesn't absorb that much heat. And there's very little heat leaking out. And so to make this problem a little bit simpler, I don't know if it makes it simpler, we're going to take a shortcut. Usually you learn the long way before you do the shortcuts, but we're just going to do the shortcut first and then learn the proper way, the long way. I'd like to go the opposite, but I'm going to just follow along this. So we're going to assume the beaker, thermometer, etc., absorb negligible heat. And only the water absorbs the heat. And so that's going to simplify this into this. Q of our system, which is the lead cooling, is equal to minus Q of the surroundings. Q of the surroundings is equal to Q of the water plus Q of the beaker plus Q of the thermometer. And the beaker, thermometer, the rest of the universe, we're going to treat that as close to zero. Very little heat is absorbed by those. This is just to simplify the problem. Later on, we're not going to treat it like this. Just for this problem. And so all that heat goes into warming up the water. So the lead cools, water warms. So lead cooling, we can use the mass times C, this is the mass of lead, times C of the lead metal, times delta T. And this is going to equal minus Q of the water. Water is the mass of the water times C of the water times delta T of the water. This would be delta T of the lead. So any heat lost by the lead is gained by the water. And so what we're trying to do is the unknown here is C. We want to measure the heat capacity of the lead. Everything else is known. So I'm going to just plug in the numbers here. So we had how much lead? 150 grams of lead at 100 degrees C. Are we out? Time? Almost. And so it's the amount of lead, 150.0 grams, I think it was, times C of the lead, times delta T of the lead. So the final temperature was 28.8. Minus the initial temperature, which was 100.0 degrees C. This is equal to the amount of water, 50.0 grams of water. This is lead, this is water, times the specific heat of water, which is 4.184 joules per gram degree C, times delta T of the water. The water started at a different temperature, but the final temperature is the same, 28.8, but the initial temperature was 22.0. I recall. Yeah, 22.0. And that's our delta T degrees C. So we're going to solve for the heat, specific heat or the heat capacity of lead. And so let's go ahead and calculate it. Here. So I'm going to get 28.8 minus 22 is 6.8. 6.8 times 4.184 times 50 divided by 150 divided by 71.2. I forgot my negative sign here. And I get a positive 0.133. See how many sig figs am I allowed? 3 sig figs, so I'll carry 1 extra. And the units here are going to be in joules per gram degree C. Joules per gram degree C. All the other units cancel out. And so much lower than water. So if something has a low heat capacity, it means it doesn't absorb much heat before the temperature rises. So lead gets hot fast. Water has a high heat capacity. Water gets hot slow, has to absorb a lot of energy. H2O has a very high heat capacity. H2O's high heat capacity is crucial for life, sustaining life on this planet. Maybe they have other solvents on other planets. But okay, I'll stop here then. Are we till 20 or 15? 15, yeah, sorry.